Lori, Karina, Ryan, and Luis. All right. We ended last class period with the thin film, and I'm going to continue from where we left off. So here's our basic strategy for the thin film problems. We sketch the first two reflected rays, and even if the problem says we have normal incidence, that of course normal means it's coming in at the normal, we're going to draw the lines for the incident rays at an angle so we can separate the rays up so they don't look like they're all coming from, going on top of each other. And label the indices of refraction in each region. Then decide whether you have a phase shift of pi radians for each reflection. Do you remember the rules for if there's a phase shift on reflection or not? Okay, if it reflects off of what? I think you said faster or slower? Yeah. If the light reflects off a medium with a slower wave speed, then you will have a phase shift of pi radians. If it reflects off a medium with a faster wave speed, then you don't. So you need to evaluate each interface to determine if you're going to have that phase inversion or not. Then you need to find the path length difference between the two rays, and from that the phase difference. And finally, you're going to calculate the overall phase difference and determine if you have constructive or destructive interference. So let's do an example. Now I've got a big picture up top, some numbers, and then something to guide us down below. So already I have drawn my picture with, even though it's normal incidence, it's not coming directly in, right? Normal incidence would have been coming like that. But then I would have had all my lines on top of each other, and that wouldn't have been any fun. So it's drawn with non-normal incidence, and we have the first ray strikes here and reflects back. So that was called ray 1. The second one is transmitted, reflects off the back surface, comes back, and then is transmitted out. That one we're going to call ray 2. And we're going to look at the phase difference between those. So according to the work that we had, the first thing I had to do is draw the picture, got all that done. What was the next step? Not the angle. In this case, we're saying that it came in normal, so all the angles are 0 degrees. But what we do need to find is the phase shifts on reflection. So delta phi 1 on reflection and delta phi 2 on reflection are the two things I need to find. Now if I look at the first one, it's going from air reflecting off of my glass. The index refraction of the glass is 1.36, which is, or film. 1.36 is just a little above water, so it's based on water. Based on our rules, is that going to have a phase shift of pi or not? And I'm going to ask you why, so don't just read up there. Make sure you know why. I'm going to pick on Timothy.
I can say that it has a phase shift, but I don't know why.
Okay. He knows that it says on the board that it's going to have a phase shift, but he doesn't know why. Sean said that the phase shift has to do with if it's a faster or slower medium. So we look up there, if it's going from n equals 1 to n equals 1.36, is that faster or slower? So if it's going to a slower medium, then you have a phase shift. So pi, because n2 is greater than n1. That means it's going slower on the thing it's reflecting off of. So now we look at the second one, going from the film to air. Do I have a phase shift of pi there? No. Why not? Yes. I'm going to use 3 and 2 here just so it doesn't confuse us. Because the one that it's reflecting off of has a lower index of refraction, then it has no phase shift. So we've done step 2. Step 3. Luis, what was step 3? Not fair, he wasn't here. Okay, step 3 was to determine the phase shift for our path. So first thing I'm going to do is determine delta L. Delta L for 2, that's the length difference for path 2 compared to path 1. Now path 1 came down here, reflected and came out. So the path length difference is going to be this part here to get back to the first surface. So how many times did that go through the film? Twice. So this is going to be equal to, I know I changed colors, 2 times the thickness, that's not a T, 2 times the thickness is the difference in the path length. Okay, so we have 2 times the thickness is the difference in path length. How do I find the phase difference that results from that? It's what? A special equation. Sean is all over this right now. I'm going to take the path length difference and multiply it by 2 pi for every wavelength that it covered, because we have 2 pi radians is the phase difference if they're out of position by 1 wavelength. Now notice I put wavelength sub f, the wavelength in the film. I did that because what's going to happen to the wavelength when the light goes into a medium with a slower wave speed? Okay, it slows down, so the wavelength becomes shorter. So the wavelength is shorter, and in fact, without showing the equation, we've seen it before. The wavelength in the film is equal to the wavelength in air divided by the index refraction for the film. Got to mark the people who came here. Still don't have Judy or Karina, the 2 people at whose table I was. Yes, ma'am.
There's an Karina's an immunology test. Bryce and I figured that out.
I figured since you came in together, there had to be some common reason. So substituting in this wavelength, the change in phase for the difference in path length is going to be 2 times the thickness times 2 pi divided by the wavelength in air over n of the film, or more simply, 2 thickness there. I just put the n on top. That's what the simplification was. The other parts were just rearranging in some random fashion. So that's the phase difference because of the length difference. So we had 2 phase different parts, one for the reflection, one for the path length difference. Now I'm going to find my total phase difference. That's not an S at all. Phase shift isn't good. Phase difference is a much better word. So my change in phase is going to be equal to the change in phase for path 2 minus the change in phase for path 1. Well, for path 2, I had 2 pieces. That's not a phi. And this one, it was just 1. So that is going to give me my total phase difference. So I'll just put in the equations we've already worked out. That's equal to 0 plus 2 times the thickness times n of the film times 2 pi over wavelength in air minus pi. So that's our total phase difference. I'm going to get 2 conditions here, one for constructive and one for destructive interference. So for constructive, what phase difference gives me constructive interference? How much? Okay, not pi, 2 pi. Constructive interference occurs when they're an integer multiple of 2 pi radians out of phase. And so set that equal to the equation I have above. I put my pi before my 2. I've never done that before. So there I just set my phase difference equal to the condition for constructive interference. And we will find then an equation for constructive interference. Now, what do I solve for? Almost always I solve for the thickness that will result in constructive interference. So I'm going to solve this equation for thickness. So solving this for thickness, I will have, let me move this pi to this side, so I'll have m times 2 pi plus pi and then I'm going to divide all of this to get the t by itself. Now on the left side, I like to divide everything by this 2 first. Divide everything by 2. And I rewrite the left side as m plus 1/2 times pi. So I divided by the 2 first. Now I'm going to divide out the pi's. So I got those all gone. And so my last step, I'm going to do it right here so I can have it on the same page. Thickness turns out to be m plus 1/2 times the wavelength over 2 index refraction of my film. So going back up to the beginning where we had the question, it said light reflected perpendicular to the film point is missing 504 and 630. I found the condition for light reflected having constructive interference. It asked me for destructive interference. Yes?
It's M.
M, okay, what is M? M is an integer. Any integer.
That goes where?
Because it can be out of phase by 0 or 2 pi or 4 pi, etc. So this here was the condition for constructive interference. I was actually asked to find destructive because it's dart for those 2. So for destructive interference, I'm going to take my same overall relationship that I did here, except for change the word constructive to destructive. And this will work for now. And now I'm going to look at destructive interference. Come on. I totally want it right there. There it is. So I have to change the word constructive to destructive here. And for destructive interference, instead of it being an integer multiple of 2 pi, it needs to be a half integer multiple of 2 pi. So we write this as m plus 1/2 2 pi. Now we have half integer multiples of half integer multiples. We have 3 halves, 5 halves. My brain has gone soft. We have pi, 3 pi, 7 pi. 5 in between those that I forgot because my brain has gone soft. Right? If you put m equals 0, you have pi. If it's m equals 1, you have 3 pi. and so on. So here's my condition for destructive interference. If I solve this for thickness, I will once again add pi to both sides. Now notice when I add pi, I now have no, that's not right. I can't believe I'm making all these mistakes. I'm going to expand this back out and not make any mistakes. I had m times 2 pi plus pi. That's what I get from this thing that I had written for the condition for destructive interference. Then plus pi is equal to 2nf times 2 pi thickness over lambda sub 0. If I take this and add them together, I have m times 2 pi plus 2 pi. If I have a difference of m times 2 pi plus 2 pi, remember m is just an integer. And so the plus 2 pi is just going to be another integer. Right, m plus 1 is an integer if m is an integer. So I'm just going to call this m prime, where m prime is an integer again. I'm only using a prime there so we realize it's not the same m I started with. So m prime times 2 pi is equal to 2nf 2 pi over lambda 0 times the thickness. Once again, solve this for the thickness. I will divide out the 2 pi's, and I find thickness is equal to m prime over 2nf lambda 0. So there's the thickness. This is where I have destructive interference. That's what I was asked for in the problem. The problem specifically said I have destructive interference at 2 different wavelengths, 504 nanometers and 630 nanometers, and not in between. And so now I need to find what thickness the film is if I have destructive interference for those 2 wavelengths. How would you go from this point? We have an equation that says the thickness is equal to m prime times the wavelength in air divided by 2 nf, where nf is the index refraction of the film. The wavelength sub zeros, these are 2 wavelength sub zeros where we have destructive interference. The thickness is staying the same. So what would we do? Well, here's one approach. One approach would be to find all the thicknesses that would give you destructive interference for 504 and all the thicknesses that would give you destructive interference for 630. And then once you have those lists, then you see what's the smallest thickness that's common to both lists. That's one way of doing it. There are others. I'm not even going to go through and do any more because it's just mathematical manipulation. Because you have your equation for destructive, you have 2 wavelengths, you can find thicknesses for each one. So I spent a lot more time than I planned on this. I spent 20 minutes on it. But I wanted you to see how we find, in a practical case, the condition for constructive interference and destructive interference for a thin film. And you see that I had a different result for for constructive versus destructive. If I had changed this from being air to, let's say it was glass, so n is 1.5. that would have changed my answers. Why would it have changed my answers? Okay, slower actually. It's going slower, so if I made that change, this would have become a pi instead of a 0 here, because it would have had a phase shift there as well. And then, continuing on, I would have had to put that pi right here, and my solutions, it turns out, would have been reversed. The solution for constructive and the solution for destructive would have been reversed. So, you have to look at each situation on its own to determine what the equation is. So that's why I said on the final exam, you won't have an equation that says for thin film interference, it's constructive in this case and destructive in this case. Because you have multiple variations, and you'll need to be able to put these thoughts together to determine what the equation is for constructive or destructive interference in whatever case you have, if there's a problem like this on the test. Let's go ahead too. Now for the double slits. We brought out the equipment and we saw how the diffraction gratings worked previously. Now we're going to make sure we understand why they work. So we start with just the simple observation of if I had two slits and I shone my laser light through it. That's what you did in lab, right? Or no, you had diffraction grating. There is a difference in the diffraction grating and the single slit, and it's pretty obvious in that picture. Look at the light up above. How does that look different from what you did in lab? Yeah. What you did in lab, it just was a red dot here, a red dot here, a red dot here, a red dot here, a red dot here. So the double slit versus the diffraction grating, you can see why we would use a diffraction grating with lots of slits, because for some reason, a lot of slits gives us a very narrow spot. Whereas if we have just two slits, it gives us a broad spot. Now, we want to determine why we get these color or the lights separated out like this. Now, from Huygens' principle, if I have plane waves, you see in the bottom of the picture there, I have plane waves coming up. They come to the hole. Huygens' principle says that each hole, this was a test question, how is it going to act? Like a point source for a spherical wave. And so we have the two-dimensional equivalent of a spherical, which is a circular wave, coming out from each one of those. And we have some locations where I have the wavefronts overlapping. And so those locations give us constructive interference. They correspond to the centers of the bright peaks. We have some locations where the wavefronts are half a wavelength out of phase, and those give us the destructive interference there. Now we want to be able to mathematically determine what those angles are. So to determine those angles, we draw ourselves a simple picture. I believe the water picture comes not right here. So our simple picture. We have the two slits separated by distance d, lowercase d, and then a capital D for the distance from the screen to the slits. Now, as I told the students in Physics 252 yesterday, we are working exclusively in the regime where capital D is much, much greater than lowercase d. That's called the far field. And the result is called Fraunhofer diffraction. Now let's make sure I understand the words. Diffraction and interference. The two words come together, and so we tend to think of the two words as one. But they're not. They're two different things. Diffraction is like bending around an obstruction. So when I have a hole and the light comes out and does those spherical waves coming out as defined by Huygens, that's diffraction. when the light waves meet and add together, so that the electric field strengths add up, that is the interference. So we have both diffraction and interference. The diffraction is occurring right here, and the interference is occurring out here where our screen is. Wherever you put it. E-N-C-E. So these are called diffraction patterns or interference patterns because the interference pattern was created by diffraction. Okay, looking at the geometry, there are some important things. I got to erase this so you can see more clearly the geometry here. There's some important things to identify here, things that I kind of garbled yesterday for the three of you. The definitions of angles. We defined the angle theta as the angle between the normal to the slits and the direction of the point we're looking at on the screen. So the angle right here, drawing in a bigger, that is the angle theta. Notice because we're working in a regime where this distance from the slits to the screen is very large compared to the separation of the slits, that means that if I make this triangle that has alpha as the apex angle, the distance between the slits is very small compared to the distance going down the triangle. So we have a triangle that is very much like this, with this side negligibly small. If that's negligibly small, that makes this angle alpha is approximately 0. Now for a triangle, what's the sum of the interior angles for a triangle? 180. If this angle is 0, and I've put this across so that I have an isosceles triangle, the two sides are the same, meaning these two angles are the same, how big are each of these angles going to be? Half of 180, because we have two angles now adding up to 180. So we have the ever enviable 90-90-0 triangle. Of course, 90-90-0 is not really true, but it's more like 89.999, 89.999, and 0.002. But that's important for the geometry we're going to use to analyze this, understanding what we've done. We made this an isosceles triangle, which means that the length of this side is the same as the length of this side, going from B to my screen and from A to my screen is what I'm defining as those lengths. Those are equal. So the difference in path length is just that. So here, this portion has been expanded out. You see the right angle there. Since this is a right angle, there's a right angle. This side is delta L right here. But using trigonometry, sine of this angle is equal to the opposite over the hypotenuse. But the opposite side is delta L, and the hypotenuse is D. So that gives us the relationship that, let me go back to not magnified. That gives us the relationship that d sine theta equals delta L, as shown right there. So the difference in path length coming from the two slits is d sine theta. Well, for constructive interference, what are we going to have for the difference in path length? Now notice I said path length instead of phase. So instead of constructive being 2 pi times an integer, it's going to be in terms of wavelengths. How many wavelengths do you shift to be back into phase? Okay? 1, 2, any integer number of wavelengths and you're back in phase. So constructive interference has to have the path length differences m lambda, where m is once again any integer. 0, 1, 2, 3, 4, 5. Minus 1, minus 2, minus 3. As long as it's an integer. So since delta L is d sine theta, I just plug that in. And I have my condition then, right here, is the condition for constructive interference. We usually write this as something like sine theta with the subscript of m is equal to m lambda over d. Now what about destructive? What's the condition for destructive interference? 1/2. So we have delta L is equal to m plus 1/2 lambda equals, once again, d sine theta. So if I solve this one for sine theta, I'll have sine theta sub m is equal to m plus 1/2 lambda over d. So we have our equations for destructive and constructive that are pretty easy to put together, as long as you understand what constructive interference means and you can do your basic geometry. So now we can go back to the picture that was on the previous page, and I'm actually going to the next one, but we can go to that picture and we can understand why we have places where it's constructive and places where it's destructive. What about places in between? How is the phase going to compare if you're in between the place where you have constructive interference and the place where you have destructive interference? Well, it's going to be partially destructive because you're going to have them, instead of out of phase by 1/2 wavelength, you're out of phase by, let's say, 1/4 wavelength. Well, if they're out of phase by 1/4 wavelength, that's my best version of a sine wave. I should get something that makes sine waves for me. It'd be better. If I take this and I move another one and put it so it's like 1/4 wavelength off, and if I add these two together, at this point here, I'm going to be at a negative maximum. At this point here, I'm going to be at a positive maximum. I'm still going to have something that's sinusoidal. It's just going to be shifted a little bit, and the amplitude will have dropped some. Because instead of adding the two peaks, I'm adding two pieces that are smaller than the peak. So I'm going to have light at angles in between constructive and destructive. It's just going to be not as bright. Hence, when we looked at that picture, and now I will go back to it. When we looked at the actual picture, I think this is it. Come on. When we looked at the actual picture, it's getting fainter as you go out. You can't really tell by looking at a picture that's getting fainter until it gets really faint. But it was dropping in intensity. So this graph here is showing how the intensity was varying with position, since we can't really tell by looking with our eye. So that's how double slit diffraction works. It's not amazing. It's not confusing or tricky, except for that we have to understand the process. Water gives us a good analogy. So here we have two places where something's just going like this to disturb the water and make waves. And if you look, you can see on this picture that in this direction here, okay, all these directions, we have nice constructive interference. Those correspond to the bright spots we saw in our film. In between, it kind of looks fuzzy because they're out of phase with each other. And so they're adding up to something much smaller, getting to a destructive interference line that's going something like now, something you notice is my lines are not perfectly straight, but they are reasonably good facsimiles of what's going on in the water. They're not perfectly straight because we're not really that far away from these 2 points. So this is really the near field that we're seeing here. We can see that they form lines of constructive and destructive interference that are going to become straight if we get far enough away. But when we're close, there's some curvature to them. That near field is actually called Fresnel interference or Fresnel diffraction. I think interference is the word we should use rather than diffraction, but I wrote diffraction. I'm going to leave it. So Fresnel is describing the near field. It's much more complicated to do the analysis of that, so we won't. We will only be doing the Fraunhofer analysis, what we've already done. And yeah, that adds nothing. That adds nothing to what I just said. Neither does that, as luck would have it. Problem. Just like we did in lab, I'm not going to do mathematically, just talk about this. I have a laser with a known wavelength, 690 nanometers, illuminates 2 parallel slits on a screen that is 3.3 meters away. So my capital D is 3.3 meters. The distance between adjacent fringes on the screen is 1.8 centimeters, so that's this distance. What's the distance between the slits? What ideas do you have to have? The first one is you have to have the condition for constructive interference. Sine theta sub m is equal to m lambda over d for constructive interference. What else? If you look at your picture, we have x and d, and here's theta 1. What relates x and d in theta 1? Tangent theta 1 is equal to x1 over d. Now, if you are a good student, you take this equation and you calculate what theta 1 is. And then you put that theta 1 in here for m equals 1, and you find what d is. A lot of textbooks say if theta is a small angle, then I can just say this is approximately equal to theta 1, and this is approximately equal to theta m. And so then I can just say lambda over d is equal to x1 over capital D. And that would work in this case because 1.8 centimeters compared to 3.3 meters, that is a small angle. But this works all the way out to 90 degrees. And if you're out at like 45 degrees, no, small angle approximation is wildly wrong. So I tend to not use the small angle approximation to solve a problem like this because usually they don't give you these small angles. I've had problems like, the first homework site I used, it wasn't a website, I don't remember what it was. It had angles that were in the range of 30 degrees and it said to use the small angle approximation, which made really big, like 15% errors in the answers. Right? That's not the way to do anything. So you need to be aware when you try to use it. Okay, clicker question. Whoops. I haven't even started it yet. Clicker question. A laser is used to illuminate 2 narrow parallel slits. The interference pattern is observed on a distant screen. What happens to the pattern observed if the distance between the slits is slowly decreased? Oh, you don't have it? I'm sorry, I was waiting for you. Okay, so we have 11, 1, and 5. It was clear that you were thinking, so I just assumed you're... Okay, the majority did answer correctly. I wrote the equation here. If D gets smaller, then m lambda over d gets larger, so sine theta gets larger, which means theta gets larger. Now, one thing I need to point out that I have not. It's pretty easy to identify what m means for constructive interference. M equals 0 is right in the center. And then m equals 1 and minus 1 is on either side. It doesn't matter which one you consider 1 or minus 1, it's on either side. But what if I was doing the destructive interference equation? For destructive, that's destructive in my writing. We have that. Now it's not symmetrical. We're going to have m equals 0 is on one side, and m equals minus 1 is on the other side. There's a symmetry between 1 and minus, or 0 and minus 1, but 0 is not at the center. And then people start to get really worried about which one's which. It still doesn't matter. It doesn't matter which way you label them. It just matters you're going to have zeros on one side of the center point and minus 1s on the other side of the center point. So don't get freaked out about it. The m is just saying it's got to be a counting number. And if they say, you know, what's the fifth one? Well, if I do 4, that's going to be the fifth minimum on one side of 0. If I do minus 5, it'd be the fifth minimum on the other side of 0. So you have to pay attention to just counting the minima and not worrying about what the m is and using that as your indicator. I point out things that have confused me in my past. Now to the diffraction grating. The diffraction grating, we got just a little bit into it yesterday with our calculus class. To do this right, you have to carefully do some work. But what we are going to look at is just simple thinking about this. If I had 2 slits, I had constructive interference at an equation given by that. We've done it. It was simple. Now, if I have a third slit, if I compare the 2 adjacent slits, I'm going to have constructive interference at the same angle. If I have n slits, they're all going to have constructive interference at that same angle. So I'm going to have constructive interference at the same angles that I had constructive interference for a double slit. Doesn't take any hard work to do that. But what happens if I'm not at that angle? When I had 2 slits, I had something like this and something like this. It wasn't completely destructive, but it wasn't completely constructive either. When I have a very large number of slits, what I'm going to have is a very large number of these things going like this. And when you add them all together, they're going to average to 0. So when you have a very large number of slits, you're going to have essentially constructive interference here and destructive everywhere else. Because anywhere that it's not perfectly constructive, you're mixing a whole bunch of different phases together and going to average to 0. That's the beauty of a diffraction grating and why we used it in lab. Because each wavelength is going to be diffracted by a specific angle. And you're going to have none of that color at any other angle. So you're able to use it as a spectrometer, something that separates the colors, and so you can analyze the spectra. Skipping over the explanation that I just gave, I swear this. Okay. Here is a nice problem for you. And this one I am going to go through. I have bright white light shining on a grating. If it says white light, what does that indicate? All colors. So here is the bright white spectrum down below. Shines on a grating, a cylindrical strip of color film is exposed at a constant radius with angles made. And so on here, we know this is 0 degrees, and here's minus 90 degrees, and here's plus 9 degrees. And then it says How many slits do I have per centimeter? How in the world can I answer that? I know I have constructive interference if sine theta sub m is equal to m lambda over d. That's the only thing I have for a diffraction grating. How can I use this information to find what the slit size is or what the separation between slits then is? Well, I only know one angle, and that's the end. So I'm going to choose that 90 degrees. What color do I have at plus or minus 90 degrees? Green. So we look down here and we say, okay, that's just the beginning of the green, right? You look here, it went from blue to green. Here we just shifted from blue to green. So it must be right about here. So let's say 500 nanometers. I mean, this does say estimate. It doesn't say calculate exactly because we don't have enough information. So we will say our wavelength is equal to approximately 500 nanometers. Our angle is equal to 90 degrees. There's one more thing I need before I can find D. What's that? M. What is M numbering? No. It's numbering 1. We call it the order, and M is telling us if it's the first one, the second one, the third one, the fourth one, etc. So is this the first screen, starting from the center? Okay, it's the third. This here is M equals 1 right here. This is M equals 2 here, and here we're doing M equals 3. So my M is going to be 3. This is the third green. So now that I have all of these, I will simply find 1 over D. 1 over D is going to be the number of slits per centimeter. So 1 over D is equal to sine theta m over m lambda is equal to 1 over 3 times 500 nanometers. And so my spacing obviously is D is equal to 1500 nanometers or 1.5 micrometers. They want it in slits per centimeter, so if I change that to centimeters, that would be 1.5 times 10 to the minus 4 centimeters, so this is 1 over 1.5. I don't know what. My brain is shot. I'm pretty sure I should be able to do this in my head, but it's what?
1 over 1.5 is 0.66.
Yeah. So that's 666 lines per centimeter is our answer. It's evil. It's of the devil, apparently. All right. Usefulness of this. Here is how we use it in basic science. You want to determine what different wavelengths are present in a light source. You use that light source, you put the diffraction grating, and you just measure the angles. Here is an example of a spectrum you might get showing lots of different colors in the blue, green, just 2 in the yellow, and a bunch in the red. That's how it's used in practice. Oh my goodness. Reflection gratings. In graduate school, I didn't use a diffraction grating or a transmission grating. I used a reflection grating. What's the difference? You have mirrors that are cut in steps like this. They're cut so that they're going to work best for a specific angle. And so you have no light essentially blocked if you're at that angle. And you have a nice broad region that's perfectly the same path length for everything reflecting off that step. So the reflection grating gives you a better ability to do spectrometry than a transmission grating. I can't believe I'm out of time. Okay, I am going to go like 2 minutes overtime because I have to. We're not going to do this next class period. We're going to do relativity next class period. If you have a single slit, light going through that slit is going to spread out. If it's a narrow slit, it just spreads out spherically. But if it's a broader slit, you will have a center region, which you clearly can't see with that color, and then diffraction that you see outside of it. So you build up a diffraction pattern that looks something like, come on. Seriously, class is supposed to end now. You can't. I'm not even going to go over the theory of it because I don't have time. Something like this. A broad, bright center region that's roughly the size of your object you would expect, and then it has peaks outside like you got from a diffraction grating, but this is from a single slit. Here's looking at the full height, the bright center. Anytime you're asked about the size of the bright center, you're going to go for the size between -1 and +1. Here's the equation that gives you where you have zeros, where you have destructive interference from a single slit. Notice A here is the size of the slit, and the angle sine of the angle times A is equal to m lambda, which means that as A gets smaller, sine theta gets bigger. So the narrower the slit, the wider the central peak is. Just the opposite of what you would have thought. And I'm not going to ask you the clicker question here. I'm going to stop there because, well, we're out of time.